So we're starting. Oh, okay. Now we're recording. So, hello everybody, Zoom participants in Zoom. We're starting the first panel discussion session of the workshop. So it's a great honor for me to be the chair of this panel session. Actually, my very first chair of a panel discussion ever. So if I make rookie mistakes, it's because I am in fact a rookie. So the theme is quantum field theory framework for quantum gravity. Yes or no? So that was the actual title, and my synopsis is QFT per GR. You want to put it in like one of those Mathematica package names. It works well. So here I tried to summarize a bunch of points that I'm going to briefly talk about. But first, let me introduce our panelists. We have Paolo Vecchia here, and we have Bianca Dittrich, Roberto Percacci, Thomas Van Riet, and Damiano Anselmi. So we will try to first introduce the topic, right? And of course, I'm just summarizing a few of the aspects that I personally think are relevant for the story, for how QFT, as we know it, fits with gravity. And then our panelists will have short opening statements each, some with slides, some without. And then perhaps I can go back to this slide of questions, and then we will open an actual discussion, eventually to the whole audience. So please be as interactive, as strongly coupled as you can be, because this is what we're here for. Alrighty, so what did I put here? Well, first, I think it's important to discuss. I mean, maybe we don't even all agree on that, but maybe we can at least start discussing what the common ground is, what the starting point is, right? We could start with, Newton's laws, but maybe it's not the best starting point. Maybe the best starting point is, like, what is the closest thing to quantum gravity we have that we can all agree on? My personal answer is gravitational effective field theory, let's say EFT from now on, as was, for instance, presented in the first talks this morning. So I feel like this is a good way to begin the discussion. So EFT, moral of the story, works well when it should work well, right? But then a few questions open up for what's beyond. So for instance, the traditional perspective on particle physics is more inclined to talk about stuff like renormalizability, right? Like, is this an actual principle that we should talk about for fundamental theory? Or is it, perhaps more on the condensed matter Wilsonian point of view, an accident, or, if you will, an inevitability of how renormalization group flow works? It's like, renormalizable interactions are all that's left at low energies after the irrelevant stuff goes away. So this is more the perspective of EFT, where it's not an actual key principle. So is it or is it not? Should we actually consider it as a valid principle for a fundamental theory? More generally, what does it even mean for a theory of gravity to be complete? Beyond having like some background doing perturbation theory on it, and then the background tells us what UV and IR mean. But in general, there is no actual sliding ruler of physical scales that is absolute and external to space-time, right? Usually, if there is any such thing, it plays a role of some sort of auxiliary scale rather than an actual physical scale. And this was actually partially discussed in some aspect of this morning's seminar by, in terms of physical running, amplitude, and so on. Now, of course, we can talk about the more technical aspects. So these are more conceptual, words that I'm saying, but there are some actual concrete things that people do, right? Various sorts of RG techniques, or perturbative techniques in the context of quadratic, for derivative gravity, because we've been told that quadratic gravity is not great. last week. And there are various ways of doing this. And then, so this is perhaps the first point, what the common ground is. Then we can go beyond the common ground and start talking about some actual issues that are qualitatively different between different approaches, different ideas. And one thing that I feel like should be emphasized a bit more is how, how essentially black hole physics points to the idea that, the standard decoupling between long distance and short distance physics, low energy and high energy physics in gravity gets sort of mixed up in the extreme regimes, right? Like because, black holes exist. But we can get more into the detail, and this has lots of consequences. Like if we try to reconcile the spectra of black hole microstates that appear from this semi-classical analysis with microscopic field theories, we run into various subtleties, right? That we can go into more in detail. This is more. I will leave this after the various opening statements to as something you can read and formulate questions over. And finally, something we should all care about is observables. Sorry? Yeah. That's good. It threatens to stop, but it actually doesn't. So yeah, I mean, another thing that I think is important is what observables mean in gravity, right? And people take different perspectives on the topic, but perhaps there are connections between these perspectives, right? There are different types of things that one can say. People talk about S-matrix elements as observables. People talk about relational observables or something else that I've heard people call eterna, namely observables that involve the whole space-time history, right? And therefore depend only on like boundary conditions of the whole space-time. Is this the only thing we have? Because clearly local observables in gravity have issues, which we can discuss more in detail. And the nature and the options we have for these observables are tied not just to mere perturbative considerations, but to actual, requirements for the full theory. Right? Just having, even if we don't actually control it, even if we just say there is a full theory somewhere, that may already have implications, because non-perturbative physics can have semi-classical residues. It can have, there can be instanton contributions to certain processes that can have implications, topology changing effects, which have dramatic implications for what observables can be, right? If there is not even a space-time manifold that is fixed, in some sort of path integral, lots of types of observables just go out the window. You cannot even define them. Perhaps you can define them up to, uncertainties that are non-perturbatively suppressed in gravitational couplings. But, if we actually insist on having a sharp full theory in principle, even if we cannot compute anything, this still has implications. Right? I think it's important. And on this train of thought, one perhaps observable that we maybe mostly agree exists in this sense, at least in some sectors of the theory, is the S-matrix, as I mentioned. And if we want to talk about, if QFT can work for quantum gravity, perhaps one way to phrase it that sidesteps all the various technicalities, RG, path integral, fields, this and that, perhaps a good way to phrase the question is, how do we encode in an S-matrix that the theory is a field theory, right? So we know how to encode stuff like locality, for example, or causality to a certain extent. And the gravity part is encoded by the fact that, we have helicity to external states, and the low energy limit is the one of GR. But what about the actual full S-matrix? Can we formulate the question in this terms? Because maybe this sidesteps a lot of other problems. So this was my very brief overview. Maybe I can give the word to our panelists. So I put them in an order that I think makes sort of sense relative to this opening slide, but also because the last two panelists will either use other slides or no slides at all. So yes, let's just okay. So these are Bianca's slides. So maybe we can give her the word. Okay. Just tell me one to, or you can just keep the little thing as you prefer. Yes.
First of all, is a tiny complaint about the question not being perfectly close. So, what is a QFT? You can ask that, and different people understand very different things about what is a QFT and what should be a proper definition of a QFT. So, of course, there's effective field theory, there's algebraic quantum field theory, which is more abstract and algebraic. There's even more abstract formulation, which I learned from my PhD supervisor. When you have a set of observables and you go and do a GNS construction, and the only thing you need to find is a partner on the set of observables, okay. And then these people would say loop quantumgravity is a QFT. Then other, which does CBT, I don't just say I think if you use quantum field theory that's a conservative quantum field theory. In the end, it was my comment on lattice QFT, and Daniela, which is also there he's coming. That's group field theory. It's a quantum field theory on a group, so that's also QFT. But I guess possibly that was not the question in the title. And so here I will present an argument which is quite basic because it's about observables. And I like this argument because it really is about fundamental constraints we might have in the observable algebra for quantum gravity. And so that is indeed the question, do local observables exist in gravity? And so that is certainly what we are very much used in standard QFT. And even the expression of John about what is effective field theory, all the unknown stuff we assume is like local. For that, you need to know what local actually means. So certainly we use lots of local observables or as a need and standard QFT if you have a fixed background, which depend on a space-time point, but obviously are not diffeomorphism in my own. So these are not available at all in quantum gravity. And I guess so far, my understanding is that there are two options, so-called relational observables, or a bit related but quite different observables at asymptotic infinity. These often use background structures of asymptotic infinity. So for me, it excludes many scenarios like in cosmology and so on. So I will not concentrate on that right now. And I will work with this concept of relation, or will say something about this concept of relational observables. And the question is, can relational observables be made to act as local observables in some sense? And so far in the literature, to my understanding, two different class of physical rods and clocks have been considered. So the idea, more or less, of relational observables is that you really have to choose something from your variables as acting as clocks or rods, or in more technical terms, it would be the same as choosing a gauge fixing. So actually, that's kind of equivalent. So relational observables you can also understand as gauge invariant extensions of gauge fixed functions. And so on the one hand, you can actually try to choose the functions of your metric field as clocks and rods. And so one choice that I did a long time ago with a student back then, we called it ADM clocks. So this is a choice of reference system where you basically say what kind of gauge fixing I have to introduce so that my coordinate system in this gauge is as much near a Minkowski coordinate system as possible. And so if you choose that, they're explicitly non-local. So these are functions of the matrix, but they involve like inverse Laplacians and so on. Another thing which people explored for some time, and there's a question, are these causal, are these local, persisted for quite some time, is a question, if you have a situation with a boundary, a time-like boundary, you can shoot geodesics from the boundary to the center. And so you can use kind of the position at the boundary and the length of the geodesics as coordinates. But then there's a question, like, if you have specific observables with respect to other fields with respect to these coordinates, would the commutator or the Poisson bracket like vanish outside the light cone, for instance? Philip Höhn and George Kirkland, and probably someone else, so that's a paper still to appear, as my understanding. I think that they showed that you can make such a choice, but this choice is also non-local. So again, there's kind of, you have to put some non-local conditions on the boundary to get actually the causal commutators. So these choices on the left are very good for quantum field theory on curved spacetime, if you want to get that from your theory of quantum gravity. You know, that is basically to the lowest order and some expansion and the Newton constant. You basically get QFT on a curved spacetime, but they're all explicitly non-local. So to higher order, these non-local terms will all show up. And so that we could say is possibly not a local quantum field theory in the usual sense. The other choice you can make is to choose scalar fields. So typically it's metascalar fields. You could choose like invariants of the Riemann tensor, and they're somehow directly 4, but it would be a very strong assumption because you have to kind of assume that these would be all take different values, you know, so that would be a very high curvature configuration. So you can show that at least classically they are explicitly causal, so Poisson brackets or commutators, classical commutators, do vanish with respect to the phase space point on which they are kind of sitting, like on the matrix. But as I will now show, they lead to a bound on the resolution between space and points defined by this coordinate system. Yeah, and so Steve Giddings is not here, but I think the complete argument is in a paper by Giddings, Marov, Hartel using covariant path integral methods. And we looked at it canonically when constructing canonical observables. And so you use 4 scalar fields as a clock, and you want to observe a 5th scalar field. So the quality of your clock depends on the rate of change under the time evolution, and that is given by the commutator of your clock field, which is the psi, with a Hamiltonian constraint, which you have in gravity. And so you get something which is the momenta of your field. And so if you want your clock to be fast, and so allowing for fast, high resolution, then you need high momenta and high energy. And if you can compute the Poisson brackets for these Dirac observables, at least to some expansion, which is kind of like a small distance limit in terms of these physical coordinates. And what you find is a usual Green's function, but you get this extra term you see there, which is something much more complicated, but in the end is something like energy of the field you observe divided by the energy of your clocks. And you can make a much simpler calculation in 2 lines for the free particle if you choose the position as a clock, and you will see the same result. So this kind of term always appears if you choose fields as clock where the momenta appear quadratic in your Hamiltonian. And so that is typically the case for relativistic field theories. There has been a kind of a fashion and canonical quantum gravity choosing artificial, kind of adding artificial dust to your system to serve as clocks and so on. And then it might not appear, but I find that a bit unnatural to use dust as describing quantum gravity. So it's possibly not fundamental. So it's similar, basically, you find it also if you start with a path integral and you find these gauge invariant variables in a path integral, look at it, 2-point function perturbed in some expansion again, which has been done in this paper by Giddings, Marov, and Hartel. And so basically now the argument is, well, if you want to have good clocks and you want to have that in a certain space-time region, you have to fill the entire space-time region with your clocks and watts, and they all need a certain energy. And so you can make an estimation, basically, which says that the size of the region divided by the squared of resolution squared has to be smaller than Max Planck, because if you do that too much, you form a black hole. And so in the end, you arrive at something which these authors called even super holographic bound. So it's the number of degrees of freedom you can resolve is very bounded in principle in a given region. And that was even super holographic. So that is basically the question: can we probe in principle beyond Planck scale? And so this simple argument is trying to define local observables suggests possibly we cannot. And there's interestingly different approaches converge on that. So again, if you go QFT, use some possibly semi-classical physics. Again, by Steve Giddings, he worked a lot on Planck energy scattering producing black holes. And so that is probably a question I have to John and other people whether that appears. So that certainly is hiding, or could potentially hide, high energy scattering. And then the argument continues, you have a Hawking radiation, and back then, it was possibly non-unitary, so it was destroying information. But certainly it's kind of hidden in a very complicated way. And LQG, more generally, we quantize geometric degrees of freedom, and that's not only in LQG, but also recently in even continuum approaches that we can sometimes, people argue that quantities like areas are quantized, in particular if a minimal area of Planck size. So we cannot probe these regions. And non-commutative spacetimes, a la Doppler, Friedman, and Roberts, use this forming of black hole arguments explicitly to construct their non-commutativity, but you get UV infrared mixing. And so here we have kind of a simple argument using observables to ask, can we really probe beyond Planck scale? And is a QFT, whatever QFT means, is a QFT picture valid there, or could it be valid there?
Very good. Thank you very much.
All right, so the next panelist, Thomas.
Yeah. So I just moved it like this.
Yeah.
Mine will be much shorter because what I did is to write down what I thought, what comes to my mind when you say QFT as a framework for quantum gravity. Okay. So I would say that you would expect quantum gravity to not be a quantum field theory. First of all, it's perturbatively not renormalizable, but on top of that, it's a spectrum at high energy is not consistent with a conformal field theory. So I just wrote down things to debate, right? I didn't work on this, but this is a known thing. So this is, for instance, a problem with asymptotic safety. So this is one of the things that came to mind when you want to discuss QFT as a framework for quantum gravity. So if quantum gravity is not a QFT, what can we learn? So the good news, well, first of all, you can think of quantizing gravity as an effective field theory, of course, which is totally fine. That's the good news. It seems to be that you can actually do this. But the bad news is that if you do it, it's not very predictable, which is the usual problem with non-normalizable field theories. So we're lacking physics, we're lacking some insight. And even if you do it, you're okay with this lack of predictability. The observable effects of quantum gravity are notoriously always suppressed by some fundamental skill. Okay, so I think that's the bad news. Let's say instead of using the word effective field theory method, what you can think of also is just semi-classical methods, by which I mean, roughly speaking, saddle point expansion. Okay. What can we learn from a saddle point expansion? Typically in Euclidean, using Euclidean methods. So the good news is that it has been extremely powerful and insightful in quantum gravity, okay? To the extent that we do not know why it works so well. Famously, I would say is, black hole entropy, okay? How come this method knows about black hole entropy? And I want to emphasize this because I'm at a conference where there are also non-string theorists, and I'm not used to this. And I would like to hear people's opinion on this paper by Ashok Sen, saying that, okay, if you claim to have a microscopic description of gravity, of quantum gravity, what you need to explain is the area law, but much more, okay? Famously, for instance, another contribution to the area law is a log of the area, right? And this log term comes with a specific number. That number can be computed using Euclidean methods, using effective, well, let me also call it effective field theory, but you need to then to match it to your microscopic description. So in string theory, what people were able to do it for a few cases. So not only do you get the area law, you also get exactly that specific coefficient right from a microscopic counting, right? So the claim is that that number goes wrong, for instance, with loop quantum gravity. So that's a place where you can see that quantum field theory, in this case, a semi-classical expansion of a path integral, has something to say about quantum gravity, can tell us rule in or rule out, maybe, quantum gravity theories. And you're welcome, of course, to disagree. I don't try to upset you. I just want to get discussion going, right? And I think in this regard, what needs to be mentioned, I think, is an amazing result, of which I'm not an expert at all. But that same method, which we, previously it was always said that if you want to resolve the information paradox, at least these are Stronger's words, you need to be able to calculate the page curve. If you do it, you solve it. Now we know differently, okay? This same approach can consistently calculate the page curve. It goes up and then it nicely goes down. And we still haven't resolved the paradox because we don't know the actual quantum state of Hawking radiation. We just can calculate using, amazingly, these path integral methods that its entanglement entropy goes up and then goes down exactly to zero. But we cannot calculate the quantum state. The state is prepared by gravity, and we do not know what it is. So the information paradox is still out there. Okay, but I just want to highlight that it's kind of surprising how good Euclidean methods are. Right. And I also want to emphasize when you go to lower dimensional gravity, saddle point expansions, and even going beyond seems to, has gone through a lot of spectacular progress. But don't ask me, there are other people here who know much better, right? And I think a lot of our progress was inspired by the CFT, but it's also independent of it. Okay, what's the bad news with the saddle point expansion Euclidean methods is that, as I said, it doesn't tell you about the microscopic physics. Okay? For instance, how is the information leaking out of a black hole, and what are the black hole microstates? Secondly, and this is an old problem, is that the rules of the game are not clear. Right? Is it in the end to some more topologies, as we say? Well, it's actually still being debated. And at least if I go to the string theory conferences, talks say about Euclidean wormholes. They either are talks about how great they are, how they do what we want them to do, and then there are talks saying how bad they are, how inconsistent they are. It's very confusing. Similarly, in this regard of, should they contribute or not, other examples of saddle points where there's like an eternal discussion, and I think Neil here is the expert. Is it, should we use a Hartle-Hawking saddle point? Should we use a Vilenking saddle point, or should we use something else? Also, this to me means that, this part of quantum gravity, the saddle point expansion, is not yet sufficiently understood. So then how far can we get using QFT framework, ignoring the degrees of freedom at higher energy scales? Because that's what I just talked about. I talked about quantum gravity without introducing new degrees of freedom, right? I would say it will always remain limited. But now I at least want to sell one particular aspect of string theory, not string theory as a description of the real world. And I know everybody always says, no, that's the only thing I care about. Personally, I do not, for a very good reason, okay? The harmonic oscillator doesn't describe the real world. The Ising model doesn't describe the real world. Without the Ising model, we wouldn't have any progress, in statistical mechanics, you name it, okay? So the thing that string theory does for you, it's a machine, and it spits out quantum field theories, which we know can consistently be coupled to quantum gravity. Whether it describes a standard model coupled to quantum gravity, we do not know. But keep that in mind. At least it does that for you. So you can always investigate, what does it tell us, right? As a toy model for quantum gravity. Maybe the actual model, I don't know. But at the moment, I don't care, right? So what did we learn then from that point of view for, say, quantum gravity as an effective field theory and so on? So we learned, for instance, that quantum gravity is only seems to be UV completed. In those cases, always with infinitely many fields. You cannot do it with a finite number of fields, right? We also learned, coming back to my first slide, that the spectrum of high energy states in anti-de Sitter space surprisingly is consistent with the CFT. So when I said it's inconsistent, this was a flat space calculation. When you do an ADS calculation, when black holes get very, very big, and they start probing the ADS scale, things change. And it can actually be consistent with the CFT, and string theory has shown explicitly how that works, like the details of it, not just the words, okay? Also, what I think it should be emphasized is that string theory has shown that ADS-CFT and ADS-CFT together have actually shown that these Euclidean methods do make sense. I was telling them, but the actual evidence is there. Like, you do the microscopic counting and it works. So all the old stories of Stephen Hawking and friends, I would say they make sense. And finally, and that's something I care deeply about, I don't say I fully understand it, but I think we have seen clear glimpses of IR-UV mixing. Right? All of the recent swamplands hype is a lot about that. So I would say there, the slogan would be, it's not all effective field theory. And if that is correct, it's great news. It at least gives us maybe a window into testing quantum gravity theories. That's what I think I had to say. Yes.
Yep.
And
All
so
right.
now it's the next one.
Thanks a lot, Thomas. We have maybe a different perspective on the relation between QFT and gravity from Paolo.
Well, I will be mentioning in some case where you need the theory of gravity, and then some case where we can use the theory of gravity to compute quantum field theory of gravity to compute observable in the classical limit. So the first example that I want to bring is that go back to this paper from 1965 written by Weinberg, in which essentially showed that the infrared divergence in a gravitational theory come only from one loop diagrams. And they exponentiate in momentum space. So the amplitude can be written W times the part, which is infrared finite. And this exponent has been computed by Weinberg by computing this loop diagram. And
yeah, we should be able to.
Yeah. And so the integral can be computed, and that's what you get. where you have in the second line a small lambda and a capital lambda. The small lambda is an infrared cutoff, and the capital lambda is an ultraviolet cutoff. And they are connected to dimensional regularization by this formula. So this was calculated by Weinberg, and then Weinberg showed that the infrared divergent that come, when you compute the cross-section, the infrared divergent that come from this diagram, they cancel with those coming from the soft emission from the external legs. And then Weinberg also showed that unlike in QED, the massless limit in gravity can be performed without any problem because of the absence of the linear divergence. Instead, in QED, if you have that electron is massless, then you have problems, the similar kind as in QCD. Another aspect that you can study quantum field theory of gravity are the soft theorem. You know that if you write an amplitude with a mean where you have many particles and one graviton, at low energy, you can write as a sum of three pieces. The first piece is over the 1 over omega. Omega is the energy of the graviton, and then you have the second term which is order 1, and the third term which is order omega, and these are the leading, subleading, and subleading subfactors, and they follow at the 3 level from gauge invariance. Now, again, in the paper by Weinberg, using the discussion that I was discussing before, Weinberg extended this to a loop level. There have been many recent papers on that subject coming from different points of view, but essentially, more or less, everything is written already in the Weinberg paper. And then in the last part, I want to use gravity as a quantum field theory to extract classical observable. So in the last 6 years, quantum field theory of gravity, or maybe better, S-matrix theory, with the property of real analyticity, crossing symmetry, unitarity, has been used to extract in an efficient way various classical observables. And at large impact parameter, one can describe the scattering of 2 black holes as the scattering of 2 massive particles. And then one can extract from the full quantum amplitude the classical observables. For instance, in the case of 2 into 2 scattering, you can extract the classical deflection angle. And it's important to, as we had in the talk this morning, it's important to realize that loop diagrams contain classical information. So the classical information doesn't come only from tree diagram, but is hidden in loop diagram. So you compute loop diagram, for instance, 2 by 2 at loop orders, and then you try to extract the classical information that is contained in this amplitude. Now, the classical deflection angle is now known up to Gn to the 4th. So it's 3 loop order or 4 PM post-Minkowskian expansion, and is given in a fully relativistic way, not as in PN expansion. Other radiative observable, like the spectrum of energy emitted by the 5-point amplitude with the graviton, are known up to Gn to the cube. And the way to compute this quantity is done using the technique of differential equation to do the loop integral that has been used very powerful at LHC. Now, interior gravity The massless particle with the highest spin is the graviton. So we expect universality for classical observable at high energy. Now GR and N equal H supergravity do not have the same behavior at high energy if one performs this limit in a naive way, so neglecting the momentum exchange with respect to the quark mass. So the quark, the mass of the particle that describes a black hole. If instead we allow for any value of Q squared and M squared, one finds universality, but the PM expansion breaks down, getting a non-perturbing behavior. So in that respect, quantum gravity or quantum field theory of gravity has been very successful to compute very efficiently many observable and avoiding problems as, for instance, the angular momentum definition that people are still debating in the framework of GR. Okay, that's all I want.
Thank you. The application of what we could mean by using QFT for gravity. Now we have the last two panelists. So who wants to go first? Because so either Damiano, maybe you can connect on Zoom, or
Damiano slides. So.
Yes.
But I had to connect.
Yeah.
Okay, so while you connect, I will.
All right, that's okay. So let's Roberto, and then yes.
I only have some scribbled notes here, and it's probably not very different from people have already said until now. So one obvious thing is that effective field theory, we all agree, is it works for gravity. And in fact, I even heard Paolo say this. There's no reason not to believe the predictions of effective field theory. Now, effective field theory, somewhat paradoxically, is the most perturbative of all field theory that we know, because the expansion parameter is the ratio of some energy over the Planck energy, and that's at least 10 to the 16 or so. It's much smaller than for any other field theory that we know. And this is both the strength and the weakness of the theory, in the sense that it means that already the leading term it's just general relativity, basically, and we know that it is correct. So this effective field theory we know is correct. Of course, the effective field theory makes predictions that go beyond just GR. But then these effects are so tiny that they are definitely beyond measurability. Okay, so that's the strength and the weakness of the effective field theory. Now, it is definitely a quantum theory of gravity, and for some reason people resist calling this quantum gravity. Now, why is that? I think it is because we have been conditioned by Einstein's theory to think that gravity is the geometry of space-time. Now, that GR works wonderfully, and so in that sense, it is true. But on the other hand, in the effective field theory, gravity is not the geometry of anything. It is a force, like electromagnetic, like a force between two charges in flat space. So there is a really conceptual clash between these two descriptions. And I think the reason why people don't want to call the effective field theory quantum gravity, they keep saying we still don't have a quantum theory of gravity. And I think the reason is because this effective field theory is not a quantum theory of space-time. So I would suggest that when people say, let's look for, we don't have a quantum theory of gravity, I would suggest saying instead, we don't have a quantum theory of space-time, because that we don't have. So beyond, if you want to go beyond the effective field theory, that is something that we may call the UV completion. And then we can ask, can we find UV completion in the context of quantum field theory? Well, let's say here. So you have QFT, and then UV completion. And in the context of quantum field theory, derivative gravity that was discussed this morning by John, this is perhaps the most conservative, the simplest thing that you can do, and it is very close to ordinary quantum field theory. And then you have asymptotic safety, which goes a little further because then you have to do non-perturbative things, so you are perhaps in deeper waters, and you are less certain of what you're doing. But it is still clearly using the same general notions as ordinary QFT. But then you can go further afield. Already Bianca was discussing what is quantum field theory. And to some extent, you could say that loop quantum gravity and, for example, group field theory, CDT, in some sense, these are still quantum field theoretic. They are perhaps a discretized version of a quantum field theory. But in this connection, let me say the following, that in order to be predictive, I suppose that in these discretized version, you must take a continuum limit. It is a continuum limit that makes the theory predictive. So in the effective field theory approach, the effective field theory is predictive only for the non-local parts, as John discussed this morning. The non-local terms can be calculated. The local terms in the effective action cannot be calculated because they are divergent. They can only be, you can only match the theory to experiment, and that determines the value of those coefficients for you. But you can't calculate them in the effective field theory. When you have a UV complete theory, like a derivative gravity or asymptotic safety, you can compute also the local terms in the effective action. Because you start from a fixed point in the UV, you have to start along a relevant direction, and there are only a finite number of relevant directions. And that means that where you arrive at in the infrared is fully determined up to just a couple of relevant parameters. So this is the way in which at least these approaches, by taking continuum limits, make the theory predictive, much more predictive than the effective theory. So that was a comment. And then, of course, there's other suggestions for UV completion, for example, string theory. And the difference there is that you have infinitely many fields. So it's an enormous expansion in the number of variables. And makes theory much more complicated. So will this UV completion still be a theory of a geometry? That I don't know. I discussed, as I tried to say this morning, my hunch is that perhaps it's not a theory of the metric, of the geometry of the metric, but I think it's more likely, or well, it's possible, or perhaps even more likely, that it's a theory of the geometry of the connection instead. And in that sense, I sympathize with loop quantum gravity and the shape of what the theory will look like depends also very much on what we want to observe. So if we want to observe scattering angles and things like that, then these very field theoretic formalism are very, for sure, the context. I mean, the most powerful tool that we have to compute such observables. And okay, I think I can stop here. So Thomas said, can we use a quantum field theory as a UV completion? He said, probably not. I say, I don't know. I don't rule it out. I think quantum field theory has been declared dead several times in several contexts. For example, in the context of electroweak theory, you know, people had to describe a massive spin-one field. And it was not until you discovered the Higgs phenomenon that it became possible to do that. And in the case of strong interactions, it couldn't be described by field theory until asymptotic freedom was discovered instead. So every time you need to discover something new. And so it's possible that also for gravity, we need to discover some new aspects of quantum field theory that we're still ignorant of.
All right, thanks a lot. Damiano, the virtual stage is yours. Oh, would you like to?
I could have mentioned
Yeah.
Thank you. So it was good that Roberto could speak before me because I agree with everything he said on quantum field theory, and I can move some steps forward because my position is much more radical and actually more conservative. I think that quantum field theory is the highest achievement of human mankind, of human history. I think there is not a bit of comparison in any other area of knowledge or approach, but everybody who claims differently is welcome to get the successes or comparable successes like the ones of the standard model and what we had before. So there is no question that the answer to the question is yes. Quantum field theory is a path to everything, I think, and I think that quantum gravity is just like the standard model, just a step ahead of the standard model. So it will be in the same framework. It will be probably the proposal I talk about tomorrow in my talk, which is also able to make predictions because, you know, we need to talk about something that can be tested. And this is hard because quantum gravity cannot be tested. That's what we think normally. Well, that's not quite true because it's true that we cannot make experiments in laboratory, but there is a universe, and that's a laboratory for quantum gravity. So, for example, if you have a theory of quantum gravity, that should be able to make predictions about what happened in the primordial phases of the universe. The theory I will propose tomorrow makes a prediction for the tensor to square ratio that is going to be measured in 10 years. And it's a very sharp prediction. Either it is that one or it's not that one. So this is what we normally do in high energy physics. That's not what people do in the realm of quantum gravity alternative proposals, which is funny because it's a domain where what's alternative have become mainstream. So it's revolutionary to be conservative and say that quantum field theory is the path and it is the only one which is going to give us the answer. So that's my position. But I also agree with what Roberto said, because years ago, what I thought was that quantum gravity is just Einstein gravity. Period. It's non-renormalizable, so what? It can make predictions for probably thousands of years. And it has limitations because it is not renormalizable, so what? The standard model has many limitations. For example, it's not asymptotically free. It's not asymptotically safe. It's not asymptotically decent. Nobody knows what it is, asymptotic. Take QED, pi to the fourth, even worse. So quantum field theory, to your title, I would add perturbative quantum field theory. That's my friend. Not, I do not think that humans are made to be so smart. I will talk about something philosophical tomorrow also. So stay tuned. If you want to enjoy that. So that's not about it. But I don't think that humans are so smart to get wherever they want. I definitely do not think that because we can have look at what humans do and have done in the history and have achieved. As I said, this is the highest achievement. Of course, it's a bet what I'm saying, because if you have data like it was with quantum mechanics, astonishing, revolutionary data, you change your framework, you change everything because you are forced. Even if you don't understand anything, you are guided by data, but we don't have data about quantum gravity. The thing I mentioned, the tensor to scalar ratio, will be probably the only quantity we will be able to measure in decades. In decades. Compare it with the standard model. And the standard model was an incredible amount of data, which is just an epsilon with respect to the data we could have in quantum mechanics, which is just an epsilon with respect to the data we have in classical physics, because anytime you open your eyes, it's a huge amount of data in comparison. But still, the standard model could give us a huge amount of data, and we don't have that. So you can make either the missing part, which is quantum gravity, is a step away from the standard model, or there is no chance whatsoever. The human being with its own intellectual limitations can guess what's beyond. I believe that with no doubt. So normally I use the approach of some philosopher that don't want to mention to not create problems, but basically a good approach is the following thing. You take what humans think or thought in history and try an approach that is as antipodal as possible to everything. You will see how many things you understand like that, and how many things you get right. So, for example, I agree that quantum field theory is the highest achievement, but not all quantum field theory. Because quantum field theory is supersymmetry. Where does that come from? Really? A symmetry between bosons and fermions. I have been, in my life, overloaded with claims that this was going to unify. I don't even remember the claims because I started to not pay attention at some point. And then there was CERN in 2012 that discovered the Higgs boson. Fantastic, but it was supposed to discover supersymmetry. People forget 1 day later how much we spent for that non-discovery, because I know it. I've seen it in my life. That was my life. It started in 1994. Do you understand what that means? And quantum field theory is a lot of other things that are gratuitous, out of nowhere. And I could mention some of the things that are floated around in these days. For example, why on earth should the ultraviolet behavior of a theory be nice? You are speculating about asymptotic safety. Why? I don't understand. Why should be a theory asymptotically safe? What examples do you have of theories that are asymptotically safe? Because the standard model is not. UCD, okay. Can we elevate one example to a prototype of everything? Really? Is this how we work? Yes, of course, this is how we work. But this is a social way of proceeding, right? And again, I think that the answer will be, and the proposal I have tomorrow is nothing more than that, a perturbative theory with all the limitations of the standard model, so it will be renormalizable. It will not be asymptotically anything decent, actually, like the standard model, but capable of making some predictions. So for me, this is the answer. And the other thing that I find very, to move to another comment that I want to make about observables, is this. When we study physics, in quantum physics actually, we talk about physics that's on shell. On shell. It's very funny, right? Because what is on shell? I asked ChatGPT a little before, to know the answer. What is on shell? Okay, something has to satisfy the classical equation of motion. I thought I was doing quantum physics. But something has to satisfy the classical equation. Oh, okay. So we are not doing quantum physics. So what is that? Of course, on shell means something only if you are asymptotic. when are we asymptotic? Never. So every approach that it has a limitation to go beyond on shell, I think has limitations. Of course, one is string theory. Does quantum field theory have that limitation? No, I will show you tomorrow. Let me make a comment on this observable thing, because it is kind of related to that. So the problem of local observables in quantum gravity is what? How do you build quantities that are invariant with respect to diffeomorphisms in quantum gravity? You have to sacrifice, one approach is, you have to sacrifice 4 scalars or 4 quantities. Because if you have 4 quantities that are functions of 4 quantities, coordinates, and you assume that it can be inverted, then every 5th quantity can be written as a function of those. Okay? And so as a function of those, you can have that the 5th quantity is observable. But this is like choosing a sort of gauge fixing. Now the question is, what are these observables? Again, as you heard, they could be matter, they could be a sort of ether, something that's spread out all over space-time. They could be built with the metric itself, and normally they are non-local things. Let me remind you that this problem is not just a problem of gravity. This started with Dirac, because Dirac asked himself, what's an electron? How do you describe the electron? The electron is a field that's not gauge invariant. Of course, in QED, A mu is nice. You can turn from A mu to F mu, the field strength, and that is gauge invariant, just with one derivative. But then you're going to do it non-abelian fields. So you put this cloud around the electron, which is this non-local thing. But you have to sacrifice Lorentz invariance. You have to invert a Laplacian. So that's going to be the This can be generalized for non-abelian gauge theories. It can be generalized to gravity. But then the price you pay is the same. So there is something that you can do here. And one thing that this suggests, this exponential factor suggests, is that you need to invert the Laplacian. Okay. So you need, can you remove this non-locality with an extra field, for example? Yes, you can, but it will have a Laplacian, not a D'Alembertian, for example. Can you use a D'Alembertian here? It would work. So you can use a D'Alembertian. Then in the numerator, you cannot have the space divergence. You have the full divergence. That works. But with the D'Alembertian, you have an extra pole, which is an extra degree of freedom. Well, that's a ghost. So the question is, can you treat those as in a new way? And that's the thing that I will talk about tomorrow. Namely, you can have these 4 extra fields that you use to build observables and build them perturbatively in the realm of quantum field theory with all the diagrammatic rules you are accustomed to, with those being neither matter, neither an existing ether, and neither being built with gravity itself. They are kind of, this is what they call purely virtual particles. Which are particles that can never be on shell. So coming back to our problem that we are on shell, we pretend we are on shell, but we are not on shell. But I asked myself some years ago if it is possible to create an entity that is never on shell, that cannot even be on shell, not even asymptotically, and that can be done, but you have to introduce a new diagrammatics because Feynman diagrams do not fit that. But you can glue together Feynman diagrams and make more complicated diagrams. And you have this thing. So basically, to summarize, in quantum field theory, you have a framework that is extremely, extremely, extremely successful. And I would like to hear it said from time to time, because this is history. Forgetting and washing out and just jumping to other approaches that are what? What do they have achieved? I don't know, counting of microstates in black holes, okay, that is, no. But there is no difficulty in quantum theory to do everything we normally do in quantum mechanics or classical physics, perturbatively and diagrammatically. Yes, you will have some prices to pay. And I will tell you before tomorrow the prices to pay, because if you want to raise objections, these are prices to pay. To make this work with these entities. There is a scale below which you cannot say what is past, present, and future. Okay, so below a scale, which I will show you is this, something like this, you cannot say what is past, present, and future. So questions about quantization of quantum field theory as a framework for quantizing space, I don't know if they are right. We measure time directly up to 10 to the minus 18. So we don't know what time is below that. With laser pulses, this is the most precise measurement of time. It's our guess that there is time below that. It's just our guess.
Sorry, Damiano, there's a question from Zoom.
Yes.
So, Philip, if you can hear us, I'm going to allow you to unmute yourself. You are unmuted.
Okay. Well, hello, everyone. Good morning or good afternoon. I'm coming in remotely, so I'm missing some of the early talks because of the time difference. So I hope what I have to say has not been already said this morning. I agree with Damiano that gravity should be a quantum field theory, and I want to give an argument. You consider the Dirac action of a fermion coupled to a gravitational field through the spin connection. You take that path, you take that action, you do the path integral over the fermions, you generate an effective fourth order gravitational theory. The question is, should you or should you not then do the path integral over the metric? How can you justify stopping the path integral in the middle? If you ask, why do we integrate over paths? When we do the classical theory, we write a classical action, we vary the action over all possible paths to find the stationary minimum, and the path integral just integrates back over that same set of paths. So we're doing all the time, we're doing classical gravity, we're varying the action over a set of non-stationary paths. We should be integrating over those paths to get a quantum gravity theory. And does anybody have any reason why that reasoning is wrong?
Was it an actual question, or was it more of a rhetorical point?
It's a comment, but it's in support of Damiano's position, and it's answering the question, is gravity a quantum field theory? And the answer is yes. If I can go a little bit further, the question that Roberto made was, well, it's not a quantization of the geometry of space-time. So where do all the geometric issues come in if you just do gravity as a quantum field theory? Well, the answer is, long before general relativity, people knew that short wavelength light traveled in straight lines. Those straight lines were the normals to a plane wave wavefront, and it was the direction that energy and momentum were transported. What changes in curve space is we can still write down wave equations, we can still write down propagators, we can still construct a normal to the wavefront, and that normal to the wavefront will be geodesic. We never have to introduce geodesics the way we usually do in general relativity, because they were already introduced differently long before general relativity. So that's the second comment. The third comment is, well, what do we do with this fourth order theory? Maybe I could comment on that in tomorrow's panel, because I've addressed the whole ghost question issue with Carl Bender, and I could discuss that.
Right. Yeah, indeed. Thank you, Philip. I think it's time to open if you're almost done, maybe.
Almost done, yes. So there are other phenomena that are predicted, other strange phenomena that I will mention tomorrow. And there is no decent ultraviolet behavior here. All things that are compatible with data, and I do not see consistency problems. But of course, the question is, again, it's a bet, so I conclude here. Since we have no data, either quantum gravity is a small analytic continuation of what we have, or we are in the realm of what is totally gratuitous. That is my conclusion. And I vote for the first exception.
All right. Thank you very much, Damiano. Let me just quickly put up the opening slide again. Oh, okay. So now you do. Maybe.
Yeah, I stopped.
So I'm going back when we do that. Well, but meanwhile, I think yes, we can open up the discussion. There are already a few. Yes. Sorry. Maybe some questions or comments from the panelists first, and then yeah. So Roberto raised the.
Yeah, I have concerning what Damiano said a moment ago about these relational observables. You are saying that we have many fields, the metric field and matter fields, and the theory is invariant under diffeomorphisms. So some of those, 4 out of all those degrees of freedom are gauge degrees of freedom. And you can take them out from the metric or from the matter. It could be either one.
The normal approach.
Yeah, so you said you sacrifice 4 degrees of freedom because they are unphysical.
I am, you have to choose. Either these are matter, or they are ghosts, because they will appear to have some unphysical pose. You have extra pose, right?
What's the connection between these poles and the fact of being acted upon by diffeomorphisms? I mean, you have a field,
yeah,
and diffeomorphism acts on the field. It doesn't matter whether it's a ghost or not a ghost, right? So you could take either one as.
And so think of some unobservable field that's unobservable. It's not matter, and it's not a function of the metric, which is. It's like think of a quantum field theory where you have a field whose propagator, loosely speaking, has no on-shell part. But that's the entity I would talk about.
Yes.
So in the propagator is just the usual Feynman propagator cutting out the on-shell part. Then inside diagrams, you have to serve to cut out all the on-shell part from associated with physical properties where that particle would appear in reality. So that remains virtual. Think of gauge theory. You have for the example of ghosts, right? Ghosts are not among the asymptotic states because you don't want them. But you know that they are not in between the on-shell, they don't appear inside diagrams as well. Why? Because you are protected by a symmetry, gauge symmetry. If you are not protected by symmetry, I show that you can achieve the same, but not with Feynman diagrams, with other types of diagrams. And so you redefine your diagram matrix, and you have that these 4 quantities are of that type. What does that mean? It would be interesting physically to explore that because it opens new possibilities of off-shell physics. And but this is widely considered. It has only been considered with 1 over Laplacian, which is purely virtual in itself, by the way. Let me draw attention on this fact. 1 over Laplacian is a purely virtual propagator. It's a propagator with no actual degree of freedom. not Lorentz invariant. There exists a Lorentz invariant generalization, one over Laplace. Now, this is just at the beginning, so I do not know what the physics is, but it's neither matter and it's neither something built with the metric in the usual way. On these extra fields, you have diffeomorphisms, because diffeomorphisms do not depend on the on-shell part. You will take a moment on how they work in quantum field.
I was under the impression from previous discussion with you that you can choose to apply what we call this Vecchia prescription, namely particles that are purely virtual. You can choose to apply it to any field. It's up to you. But now you are saying it is that you must apply it to the ghost, or that it is convenient to apply it to the ghost. Yeah,
you must.
Otherwise,
otherwise those are ghosts or extra matter that change your field.
Okay.
In those cases, you must.
Okay.
Are there any other comments from the panel? All right. Well, yes.
Sorry, I couldn't hold the question.
Yeah, you clearly have something to say.
So, no, I mean, already it's mentioned by several panelists, and also you mentioned in the Ivano about gravitational path integral. And then connect to the Hawking radiation and everything. There is something not clear here. Gravitational path integral, when people talk about its Euclidean space, okay? It is completely non-trivial to connect it to some Hawking radiation happening in the Lorentzian signature or cloud space-time effects. I do not understand whether it is absolutely clean to whether we fully understand the meaning of path integral in Euclidean space and apply its implications to the Lorentzian space-time. And that's one question. And I have a comment. Whenever we speak about the information paradox, Thomas, you presented, well, all the references you quote, it's in asymptotically flat space-time. But all the papers, introduction starts there in the first few lines, and then it jumps to asymptotically ABS spacetimes, and it jumps to very complicated frameworks of theories. If the problem appears at the fundamental level of understanding quantum fields in curved spacetime, why do we complicate life and just say that, okay, the problem is solved somewhere else, and then it is solved?
No,
why do we pretend that?
We didn't say that.
At least, if there is
the calculation by Al-Hari that I mentioned, this big insight that the standard path integral calculation does give a page curve going up and down, that is valid for flat space boundary conditions.
That is calculation is done in the Euclidean signature, the Euclidean matrix.
Yeah. So
the
idea of preparing quantum states through analytic continuation.
Well, that's still again my question. I already phrased my question. So how can we believe something done in the Euclidean path integral if it is well defined, if we well understood in the context of gravity? Of course, I understand you can understand path integral.
Maybe Neil can comment. I would just want to say that there are open questions in making the Wick rotation. But then, as I said, the rules of the game are not always clear, but sometimes they are clear, and then it gives very sensible results.
I think the open questions are the center stage rather than claims about we solved the problem, or the problem is solved in some way. But anyway, the question is about this open question.
If I can add something, maybe asymptotically, if you take the case of large black holes, it is, space-time curvature is really small, and therefore the Wick rotation is more like it works in quantum field theory than in wide quantum gravity.
Let me ask, hasn't Marov done something like with the Lorentzian path integral and the island paradox? I think that
you have worked most on it, but yes, people have been. Well, maybe you should comment. I mean,
I mean the island paradox. The island.
Yeah, there are also Lorentzian pictures.
There are Lorentzian pictures for them. So there are some Lorentzian calculations.
Yeah, awesome.
In asymptotically flat spacetimes.
Well, first is a general remark about that. It's like what happens where the resolution comes from including
This replica
trick, these topology changing things, and in particular, if you go to the Lorentzian signatures, in fact, this topology changing things comes with a light bone irregularity, which Renate knows well. And so if you do it in Lorentzian, this light bone irregularity gives you a complex term in the action. And that's actually basically the entropy contribution. So there, in that case, the Lorentzian framework is basically essential.
All the topology of spatial black hole changes.
It's not a change, it's a replica trick. So
You calculate the entanglement entropy of the radiation.
So what does it mean? It's not very clear. So in the replica trick, you take copies of your stuff. And so suddenly people say, you have these two copies and you could consider like the trivial factorization. But actually now you should glue instead of this, you should kind of glue this. And maybe that is a replica calculation. Right. And so I don't think we know what's the interpretation of like taking this funny gluing rule for the replica copy means. So it's a bit hard to answer and why we should include it, but that's how it basically works with the page curves that for this branch, the settle point in one copy in one version is essential, and for the other branch, it's actually the contribution from the funnily glued.
So you could summarize as saying that Hawking's calculation, which was quantum field theory in almost flat space-time, because a very big black hole has extremely low curvature horizon. You can reformulate that calculation using a path integral, saddle point expansion, and then the insight of the last 6-7 years is that people actually forgot a saddle point. And that saddle point starts to dominate, especially for the late time entanglement. And then you exactly see that the page curve goes down. So it doesn't mean that we have understood quantum gravity, but it shows again how powerful the saddle point expansion, the path integral method is. But maybe, I don't know, other people, I haven't done these calculations, but I'm sure some people here know more about how bad it was to use Euclidean methods. I would be...
There is already a conundrum there. In the Hawking calculation, well, you take the Penrose diagram, you take the part of the Penrose diagram, which is black hole formed by collapse. That's one calculation. And you go to Euclidean time, then you end up with a quantum state, which requires both the parallel region as well, your entangled state. So that means the picture already differed from the standard QFT calculation and to going to the Euclidean method, path integral method. So even in the simplest setup.
Yeah, but if you ask that, how bad is it to take Euclidean or to take Lorentzian? I think part of the answer is that indeed the result comes only from evaluating this action on a settle point.
Yeah.
And for that case, you make even, I don't know, I think nobody is really able to check if these saddle points, if the contour actually can be deformed into these saddle points, either from the Lorentzian or from the Euclidean. So it's really just literally taking the saddle point.
Yes.
And so for that, it doesn't really matter if you are Euclidean, if you start Euclidean, or if you start Lorentzian. And I don't think anyone has computed the one loop contribution, but I'm not sure. But it's basically this. So it takes a saddle point, and for that it does. I don't think it matters too much.
I think at this stage it's guesswork.
But it does not mean that the Euclidean path integral is well defined. It's not well defined.
Yeah, but nobody here said so, right? We just said the saddle point expansion, the exponent,
But in the end, I think the bullshit thing is to take your action, evaluate it on this saddle point, which is basically almost a classical solution.
But this is guesswork. Is James, I want this saddle point to be
so it's only
that's all. There's no justification for that.
As I said,
I'm completely amazed that in recent literature, we wrote these papers showing that if you believe the Lorentzian path integral for gravity to be fundamental with the Hawking saddle, it's not relevant to the constant. And part of our argument is that, which came from Teitelbaum's papers in the early 80s, is that he showed quite convincingly, for many, many reasons, that the integral over the lapse in GR needs to go from 0 to infinity, not minus infinity to infinity. he wrote some very beautiful papers about that, which people then forgot. And so we took his prescription seriously and his argument seriously, and we showed that hardware Hawking was not the relevant saddle point. That created a lot of back reaction. But I think we were right. But what I'm amazed is that in the recent literature, people, particularly Ed Jacobson, is writing a paper saying that no, the lapse integral must go from minus infinity to infinity. And if you take this point of view, I mean, this fails for field theory, for the relativistic propagator of relativistic particle. So my impression of the field actually is moving backwards, that people are forgetting things which they knew. And now saying the rules are, we will make up the rules in order to get the right answer we want. I'm afraid that's.
But given the context of the discussion, could one do the following question I have? So you have this discussion on how to set up the path integral, how to properly define the quantum field theory.
Yeah.
Imagine one has some model that you know is at least consistent of quantum gravity, which could, because it's maybe not quantum field theory, might not describe our universe, but nonetheless, you know it's consistent. Could it shed light on a discussion of which saddle points contribute? Because, for instance, I thought there exists examples, say, in well-defined or supersymmetric theories, which are decoupled from reality, but as toy models, where with ADS-CFT you actually knew that sometimes Hawking saddle points do contribute.
Well, I think that from what I've seen so far, the question is so poorly posed. Usually people don't explain if they're calculating a partition function or a propagator. These are very different things. And in much of the literature going on now, they are not differentiated. So I think one has to ask very clearly, what are you trying to calculate?
Right.
Is it, and then is it well defined? And at the moment, there seems to be massive confusion.
So what's wrong with Coleman's original suggestion, saying, oh, if you want to know whether a saddle point contributes, you start by saying, what's the matrix element I want to compute? This fixes boundary conditions. And then you check stability of the saddle point. And normally then the law is if there's a max one negative eigenmode, the saddle point should contribute to the specific matrix element that you want to compute. So are you saying that somehow for gravity, we do not know whether Coleman's rule makes sense? Is that what's at stake?
Yeah, I mean, the kind of theories Coleman was discussing are, have positive kinetic.
Right, so it immediately out of the window.
Yeah, conformal mode breaks that. So I think, just relevant to the discussion, doesn't resolve anything, but there's this paper by Oxidich and Siegel on quantum fields in a complex metric. If you're going to use saddle point methods, you need to complexify things. So they're kind of going halfway, but complexifying the metric and ask, in which complex metrics does QFT make sense? Is there a chance that particle converges? Their starting point is Euclidean QFT, and then they complexify, and they say basically the maximum angle you go is 90 degrees, and Lorentzian is a limit, so the real world is this sort of funny limit of the Euclidean. My point of view is that the real world is here, and that actually it's 90 degrees on both sides of that line. Makes sense. So I think even that so when you do gravity, you have to deal with the kinetic term as the rock side for the conformal. And it appears to me that you can always take the Lorentzian path integral as a definition. It's wildly oscillatory. So the only way to make sense of it is to deform the contour at large field values so it converges. But then it seems to give unique results. It's just difficult, much harder than the Euclidean one.
Just one comment.
But it has a chance of existing.
Right.
Which Euclidean one clearly doesn't exist.
But I must say there exist saddle points where the boundary conditions are such that by stroke of luck, there's no conformal factor problem. Right. Because usually the conformal factor problem is in a homogeneous mode.
Absolutely.
And there are boundary conditions where you put that to 0. So at least there, the discussion should be.
But you won't
more
find
well.
anything interesting in those cases. The interesting cases are precisely where there's the instability.
Are you guys done with this?
Sure.
There seems to be another comment on Zoom. Are you gonna? Okay. Let's go with that. Yeah.
Oh, okay. I'm not quite sure. I couldn't quite tell who the speaker was. Was that Neil that was just speaking? Yes. Okay. I wanted to comment something on Lorentzian path integrals. There was a paper written by Hawking and Hertog back in the early 2000s. They wrote down second order plus fourth order scalar theory, and they showed that the Euclidean path integral existed without any problems. They also noted that when they continued to the Lorentzian path integral, it did not exist. What that meant is that the Wick contour from Euclidean to Lorentzian failed. And if you ever want to do Euclidean field theory, you always have to be able to show that the circle at infinity in the Wick contour doesn't alter the result. And they've found a working example where it does. Now, what I then did was I asked, well, suppose I've got this Lorentzian path integral that doesn't exist. Can I make it exist by continuing into the complex plane? And the answer was yes, that you can find contours in the complex plane for which the Lorentzian path integral for second order plus fourth order quantum field theories does exist, and there are no terrible oscillations. And I've also used that to use second plus fourth order theory as an ultraviolet completion of the second order theory. That's the comment.
I agree with this.
Great. So maybe yes, we can move on to a different topic since we have about half an hour.
Yes.
Great. So anything else, people? Whoa. Okay. So who is okay? You may go first, and then John.
Okay. So
I have a very, so that everybody.
Okay, I have a very simple and trivial question related to the issue of local observables, basically. So the observables that we actually measure, like what is measured in LIGO, or we measure some gravitational field strength, the standard gravitational field, etc. Do these qualify as local observables or not?
Well, to some approximation.
Okay, so the claim is that these do not fit within quantum gravity. The quantum gravity will not allow us to calculate these observables. Is that the claim?
No, I mean in practice, right? In practice, you could claim we always measure relational observables.
Yeah.
Because I automatically kind of always have, look. I always have the time there as a clock, and it's a physical system.
Okay, so if that is the case,
I always know what my position is, but relative to like the Earth, the Sun, and so on.
Good point. So if that is the case, then what is the fuss about local observables not existing in quantum gravity?
So here, I mean, as I say, so here I do make reference to things which are macroscopic objects.
Yes.
So then the question, however, is if you want to go, think of Planck scale experiments, if you want to go there, is something like phi of x, something which we can measure, and what is x? So in this context, it's really that we are so much used to standard field theoretic observables, which are just phi of x, and phi and x can be an arbitrary real number. And
Well,
there's infinitely many of these
even in
things.
field theory, we measure correlations, which are relational, basically.
No, I mean the standard correlations are phi of x, phi of y.
Yes.
So you have x and y, and in quantum field theory, like the behavior and the distance x minus y is super, super important. But you don't have x and y. You can express it again more geometrically. Renato will might talk about. But then you have to average over, like, again, you have to average over you can keep the geodesic distance constant. So that is, again, something different. And in the end, you average over all configurations. So in some sense, it becomes quite non-local.
Okay. So now there's a practical issue, which is that whenever we do quantum field theory, which is extremely successful, as was pointed out by Damiano, we never claim that I will believe in result only if you give it to me non-perturbatively.
Yeah.
Everything that we know in quantum field theory, all the successes is perturbative. Okay, we don't know how to calculate non-perturbative in the sense of like real non-perturbative electroweak effects or QCD effects. Everything we have a perturbative vacuum, we calculate around that. Maybe we can talk about some instanton, etc., which is again like the perturbation theory around them. So, and that's all the success of quantum field theory comes from there. Now we come to gravity, which we do not even understand perturbatively, it's not normalizable. And then we claim that no, you have to give me the answer non-perturbatively, otherwise I will not believe you.
No, I mean, the history, I would say the history was because it was non-renormalizable.
Yeah.
People started to consider non-perturbative approaches. And indeed, like for me, like understanding, possibly quantum gravity as a quantum theory of space and time, that's very attractive. At the same time, is very hard. But also, I would disagree that it's completely impossible because there is progress. There's, Renata has interesting progress.
It's definitely very interesting.
So, but that was the history because it was non-renormalizable. At least for a long time until maybe effective field theory became more standard, but say it was before my time in the 80s, and maybe Renata can comment. Like the logic was that we have to look for non-perturbative theories.
Yeah, so this I understand.
Then if on top of that, again, traditionally, these non-perturbative approaches traditionally also came more from people doing gravity and being very convinced of Einstein's vision that a quantum theory of gravity indeed means a quantum theory of space and time, and that this should be something very non-perturbative. Of course, and I will talk about it, there will be always a challenge. Sometimes you have a super complicated non-perturbative theory. And I see it as key challenge in all these fancy quantum gravity theories to be able to calculate something and to develop, in the end, some kind of perturbative scheme. And so there are kind of very wide truncations you can make, but then we will all discuss, is that the correct truncation and so on. But in principle, these are also done. So like scalar to tensor or the influence of the CMB, okay, they have calculations in LQG that say something about that. Do I trust them? Maybe not necessarily, but there are such calculations also done and non-perturbative frameworks.
This is a very good point you made. I completely agree with you.
Yeah, and so I do see that as a key task for non-perturbative approaches is indeed to not to speculate endlessly of what could the approach be, but to develop calculation tools, to develop calculations.
Very good. I think this is perfect. This is a very good point that you made. So then the question becomes that, shouldn't we then expect that, okay, we talk about observables only after we develop the perturbative approach? Because whenever
talk about observables only after perturbative approach,
so you have a theory. Suppose you have a theory of quantum gravity. Okay, in that basic theory, space-time is quantum. So it has nothing to do with our intuition basically, and we understand everything relational, everything from in the context of a fixed space-time, which is classical. And we know that, as you pointed out, any quantum theory of gravity should be able to give you a completely classical looking space-time in some approximation. So why wouldn't one expect that, okay, you all these questions about observables, local observables, etc. You should pose those questions after you have developed this framework where you have a background description, classical description. Then you talk about observables and all that.
Yeah, I understand that point of view, and that is one point of view to take. I did this work on observables, okay, during my PhD, and was new. And back then it was actually that people told me, like, there's no diffeomorphism invariant observables in canonical quantum gravity. So, and then I showed that there are actually lots of diffeomorphism in principle. It came from, back then I came from canonical quantum gravity, very non-perturbative, where the idea of kind of constructing your Hilbert space and your theory often starts with the idea that you have to find a quantization for your observable algebra. And so it starts with observable algebras. Also algebraic quantum field theory. Okay, I disagree on what they do in the case of quantum gravity, but it always starts with the algebra of observables. And again, the argument I presented, I find it nice because we do agree we need observables. For me, and taste is very similar to the uncertainty principle, which kind of is very theoretical, but you can derive or argue for in various ways. And of course, I guess you could also have argued against the relevance of this principle, but it's a very important principle. And so indeed, it's kind of, I think it's, yeah. So you could see it, if you would understand what can be observed, it could inform you what you should put in your theory. And so here, indeed, where, as I mentioned, like Anu actually did it like for the free particle in the time of arrival, and he got what he called an additional notion of uncertainty, which was only in energy, but only in motion. Yeah, energy. And I have examples where knowing the observables could indeed inform your quantization, and that is an example where people would used to tell me or used to say about observables that we know that there's kind of chaotic solutions or chaotic sectors in GR. When we sent the paper, apparently it was very much debated, but by half the referees. But and these observables, these relational observables, always require, if you write them down explicitly in the canonical theory, always require to solve the theory. So we consider basically not really an chaotic theory, but an ergodic theory. So your space, your time trajectory would fill your phase space densely. And that's why you would say, because observables in that context would have been properties of your trajectory, but it fills your space-time or your phase space densely. So there is no smooth observables you could write down in this example. And that was with Philip, and Philip was saying, we ruled out canonical quantum gravity on community. And I came and say, but if you use for your quantization an unusual quantization scheme, which is used also in loop quantum gravity, it's an alternative representation of your commutation relations, where you only have exponentiated, like either the exponentiated momenta or the exponentiated x. It's called Bohr quantization. Nothing to do with the physics. Physicist Bohr, but it's a mathematician Bohr anyway. Then you can quantize it. And so that was really an example where knowing the structure of observables informed your choices for quantization. Again, that is an ideal situation where you could make this progress explicitly, and it might be a bit unrealistic. But that's certainly an example where observables inform you, or the algebra of observables or properties of observables inform you about how to formulate that. And as I mentioned, like these non-commutative spacetimes, they're also motivated directly from black holes form and you cannot measure certain things. If other people will want to comment, many discrete approaches are kind of possibly formulated with expectation that there should be some kind of distinctness, and so that you cannot resolve beyond kind of scale. So.
All right. So, is there follow-up immediately on this?
No, it is not a follow-up. So probably John.
Yeah, because John had something to say earlier.
Yeah.
I just have actually, it's a simple question. It's not a comment, and it's for Thomas. It's basically on your opening slide. You had the statement that you didn't feel that gravity would be a quantum field theory because at high energies it's not a conformal field. And I'm just wondering what the thought process is behind that. It's not a condition I would normally put on the.
It's specifically for asymptotic safety. It was an argument by Banks, Haroni, and some other people. Just that the entropy dependence on the energy doesn't work out. And if you put it in ADS, it does work out. But then it's corresponding to a CFT of a dimension lower, and turns out that that's how holography indeed works. Right? It's just an observation on.
Is there something to say about this?
No. Continue finish the comment.
No.
Sorry, but it may be helpful to elaborate. I think, if I'm getting it right, the argument is the entropy of black holes grows exponentially.
Super exponential.
The mass squared.
Yeah.
And
So
you never get that in the CFT.
Yeah.
That's the argument.
Yeah.
Asymptotic safety in the UB is not necessarily a conformal field theory, so the argument doesn't apply so straightforwardly. So we know in order to have a UB completion, the requirement is to have a fixed point, but a fixed point only implies scale invariance, not necessarily conformal invariance. And indeed, it's unlikely that that is realized. So it is still possible, of course, that it doesn't work out, but it is not so straightforward. Because you cannot apply the scaling with the conformal field theory.
Right. Not sure you heard it, John. So
I heard it, but I think other people understand the answer better than I do.
Well, the argument is that if it can be the fixed point can be a field theory with scale invariance without it being conformal field theory, and then I think the dependence of the entropy, maybe that argument doesn't work, but I'm not so sure. I think Ivano, you had.
Well, I mean, maybe the dependence is roughly similar, but even if it's not, the high energy scattering is still our law, as John mentioned. Whereas the density of states of black holes gives you like an exponential suppression in the high energy. But I think Anna wanted to say something.
Yeah, I wanted to ask a small follow-up question. What is conformal symmetry in gravitational theory? What is the meaning of conformal symmetry? Because
well, if you say the word QFT and you say the word conformal, then you just say that the conformal group is realized as a symmetry. So
but it's
with
a
Hamilton. Sorry.
curved space, anyway. Conformal group can be well defined in the flat space, but if the space is curved, what does it mean? I mean, if the space is not specially curved but arbitrarily curved.
But you could say the same thing about dilations, but it's in this auxiliary scale that people talk about.
In dilations, in principle, you can define what does it mean because you just take coordinates and rescale them. But in conformal group, you cannot make a generalization very easily of precisely conformal as a global symmetry. You may suggest value invariance, but it's much more. It's different.
Scaling coordinates needs some sort of origin, which is in general you don't have. Right? But was there someone raising their hands? Did I see someone? Okay, maybe I was.
But maybe.
But yeah, I mean.
I agree with what you said.
Okay.
Right.
But
So, yeah.
maybe reconnecting with since we are speaking about asymptotic safety and conformal field theory, and so Damiano mentioned why would we ever want to have asymptotic safety? Well, first of all, we have a particular case of asymptotic safety in the standard model, which is obviously asymptotic freedom and quantum thermodynamics. But more generally, even forgetting about that, the idea if the framework works, is that you would have a way to predict Wilson coefficients, to reduce the number of parameters in your model. So there is only, I mean, you mentioned, you yourself mentioned that a theory of quantum gravity, a theory of anything needs to be predictive. And the predictive power in asymptotic safety is exactly implemented in this way. So as soon as you have, as long as you have a fixed point with a finite number, with a finite UV critical manifold, then you can impute your respective action and have only a few relevant parameters and a few free parameters, and then you can compute your scattering amplitudes in terms of a few parameters that then you need to fix by variance. So that's the reason why you would want a symmetry principle. So you want a quantum or classical scale invariance in the UV, and it is the symmetry that reduces then that allows you to make predictions. So that's why we want that. Yes, go ahead.
I understand that. That's the premise of asymptotic safety. That's predicated on a list of assumptions that you recall that I think has almost zero chances of being realized in nature because of the analytic confirmation from the rest.
Can you spell that out a little bit more?
Yeah, I asked during my speech, what is another example where that happens? I
in 4 is 5 or 6 because in higher dimensions.
No, in physics, sorry.
Yeah, okay.
Depends on what you mean by
yeah, exactly, because quantum field theory is simple, and quantum field theory has been unfortunately broadened a little bit too far, I think. So when I talk about quantum field theory, I think that quantum field theory that was successful, there is one, it's called standard model. Then you can speculate about adding tweaking something beyond standard model. What has been successful so far? Nothing, I think. So for example, you have U1, SU2, SU3. What's the indication that there is any unification there? I see none, but this was a mainstream for many, many years. What is the indication that there is a symmetry between bosons and fermions? Zero, but that has been another sociological event. Many promises, no achievement. There is this case of asymptotic safety. You take, again, one case, for example, the unification of the electroweak, so-called unification, and you promote it to the unification of the whole forces of nature. So personally, philosophically speaking, I do not believe in symmetry. I do not believe in symmetry as a principle, because not because I don't like it, also because I don't like it, but because it has very limited power. Symmetry is just our narrative of something we have difficulties to formulate without a symmetry. Like take gauge fields, you have 2 degrees of freedom, but you need 4. That's just our problem. It's not. This is our way of describing it.
But this is specific to gauge symmetry, not to global.
Gauge symmetries, yes.
Yeah, gauge. Yes.
Oh yeah, global symmetries are okay because you can break them.
I think one should be careful, probably, not going too sociological or philosophical, but so regardless of whether supersymmetry is realized in nature or any other symmetry, it is crucial for humanity to study quantum field theory with a lot of supersymmetries. If we cannot understand, if we cannot understand N equal 4 super Yang-Mills theory, you should not hope to understand the standard model a little bit beyond the way we do it now. Okay.
You're joking, right?
I'm not joking at all. If we ask students to calculate something in the Bachelor of Physics, there will be spherical symmetry. If they cannot compute something with spherical symmetry, you do not want them to solve anything else. You need to first learn a harmonic oscillator before you can understand the anharmonic oscillator. So the way supersymmetry is used currently, I think it's extremely important. It's to get exact results in quantum field theory, to get a glimpse into how quantum field theory works.
And we should not conflate that with this promise, which, by the way, a lot of people in our field never bought, that we would see Susie at LHC. This was a promise of a few people. And you should
there was the pay raise her.
It's the new thing.
We're still okay. We're using the convention. Okay, any further? Okay, you have some.
And since you asked for specific examples of asymptotic safety, I mean, go to condensed matter. You have fixed point in condensed matter 3D. They are the same fixed points.
Applause. Fantastic. And however, I want to do fundamental quantum physics. This is no way in argument. I'm sorry. No way in argument. That's the beauty. I don't want to use this because it's has been abused by string theory. The theory is beautiful. One of the ugliest theories ever produced. The power, let's say, of quantum theory is precisely to be so constrained by a few requirements that you cannot propose any new idea without destroying everything, basically, or instead in condensed matter, like many other situations. For example, why should we have unitarity in condensed matter? Why? There is always a reservoir of everything that can communicate with inside, outside. So you have an enormous freedom there, and a lot of examples where I agree, asymptotic safety for that is interesting. But we're talking about asymptotic safety for gravity as a fundamental theory. And I don't even think that the time is fundamental, because it's something we experience here, and experimentally we go to some scale. It's very, very hard to measure time. Just think of it. I don't know if this is just one second. Just to compare the prediction of our measurements of space and time, because we normally think of space and time is space-time, just one thing. But the direct measurement of space are 10 to the minus 17 centimeters. And that's from the gravitational wave buildings. And for time, it's 10 to the minus 18 seconds. So there are 10 orders of magnitude difference if you use the velocity of light to convert seconds into centimeters, which means, which is obvious, of course, because time is in our mind. We don't see time. That's a comparison between a perception of a moment ago with an actual perception in front of us. So obviously, the measurement of time is so imprecise. How can we promote it like that into something as fundamental? So I insist on this because even when tomorrow we'll talk about a prediction about the tensor to scalar ratio, you can find, I think, 10,000 predictions about the tensor to scalar ratio. And in 10 years, we will know, and everybody who got it right, because there will be somebody, will come up and say, but if you don't have the powers in cosmology that come from high energy physics that are restricted, because you have to have, for example, a normalizability, you can have non-predictive theories like string theory, for example, which is non-predictive because there is no string theory. There is a manifold, an infinite parameter manifold, or 10 to the 500 parameter, I don't know, I don't care, but of theories. And where, if they want to make a prediction, please do it. You have 10 years.
I was also comment on extra examples, but
maybe this discussion is good for Friday. Ivano, there's a panel discussion on the string parameter. It's only on this moment.
In terms of still examples within quantum field theory, I mean, there is still the Gauss-Duo model, which is asymptotically safe.
I know, and the models, I've studied them. They are very interesting things.
Yes.
But we're talking about what is realized in nature.
Yeah, but what is realized in nature, then we see, I mean, with comparing predictions with observations, but in principle, it is a possibility, and mathematically it is possible, and at the level of Wilson normalization, we know that the principle, I mean, the normalizability is about fixed points with a finite number of UV attractive relevant directions. So, and it is not really about this, or maybe you don't like symmetries, other people like symmetry, but it is about principles, okay? And every quantum gravity theory has a certain number of principles, and that allows us to make predictions and This is why, at least like from the point of view of asymptotic safety, the principle of having the quantum scale invariance is powerful. Okay. And
I don't accept
and
that. It is a possibility.
It is a possibility.
Indeed, what I said is a bet. I just think that my bet is safe.
But so I don't but what I find confusing, because I agree with what you're saying, is that you use the words, I don't think it's likely, and then you try to argue why something is likely or not. And every time you argue,
From the standard model.
exactly. So for you, you say, I know one quantum field theory out there, it's realized in nature. But if that's the only one which you're willing to argue with whether something is likely in the space of quantum field theories, that's very strange. That's a single element in the space.
Very strange.
No, this is not how physics has worked.
Yes,
No,
it
you're
does.
by
You compare with
so okay, because
the
then
amount of data of the standard model and the amount of data of string theory.
all right. So from now on, we can only use the standard model as a study to quantum field theory to argue whether something is likely or not.
We're essentially out of time. So yeah, I was
a little bit over time.
It was about to say, is this about what we were?
Yes.
Just a comment.
On this.
Yeah, on this.
Okay, and then maybe very quickly on
Damiano said that string theory doesn't have any predictions. Well, there's a small tweak to that. String theory predicts everything. Yeah. So that's the problem. Inflation is possible, no inflation is possible, and everything is possible in string theory.
No, sorry, people. This is not this is fake news. Fake news.
I think just one we will discuss this on Friday.
There's a non-trivial prediction of string theory. Okay, we call it prediction at position or whatever. It tells you that all the fields relevant for description of nature must be massless at the fundamental level. This is highly important. Nobody expected it before standard model. In standard model, without Higgs mechanism, you have to start from everything being massless, except for the Higgs. This is a high non-trivial fact, and it so happens that string theory gives you precisely that. It tells you that no, at the fundamental level, you have nothing at your disposal in the low energy theory except for massless fields. I think that's a very interesting fact. Okay, one may believe in string theory or not, but this is an interesting outcome of the theory that you get. It's a fact, basically. You cannot
that's great, but this panel is not about strings.
Yes, that will be actually a panel discussion.
It's not about strings, but there's one question. So renormalizability is important. Why? Of course, in string theory, the argument is that renormalizability is not important. So I think this is relevant. But renormalizability is important.
Is that? So yeah, sorry, your point about renormalizability.
Yes. Well, question is a QFT framework yes or no. But let's talk about renormalizability. How many agree that renormalizability is an important criteria for quantum gravity?
Show hands.
Show hands.
So,
then it's as a QFT, so okay, accept that it's
I agree. I agree. Just as a tool because it works so far.
Okay.
Because in the past, I used to elevate that for other things for principles. Later, I learned to be more cautious. Just because it works so far, and it might work also for gravity. As a bet, I think that as a work hypothesis, but it's not a principle. Just note this funny fact that everything that we call principle is normally the last thing you achieve when you gather many ideas. That's not the principle you started from. And this is
if you leave it just a school, you have to find a new principle. Okay, if you leave this, what is the new principle?
I don't live for principles. I just live for.
But if you don't have principles, how do you organize your predictions?
As long as it works.
If I want, I can tell them. But it takes.
No, maybe tomorrow.
Mostly it's random. That's the answer.
But then,
uncertain.
Oh no, faith.
Yes. Yes, you
I apologize for missing the first half of the discussion, so maybe this question has been answered. So it's for those people. So the question is QFT.
This is not really a well-formed question, actually. QFT framework for quantum gravity, yes or no? Correct. So for those panel members and indeed participants who think the answer to that question, however they interpret it, is yes, is the path integral for this quantum field theory for quantum gravity, does it include a sum over manifolds as well as an integral over metrics? And you can say, okay, so time is short, so Chair, maybe you could just, yes or no, yes, yes
or no.
So those include, yes.
Summing over manifolds, yes or no?
What
Topologies.
Topologies.
I am a perturbative person, so I don't know.
I'm confused about it.
I didn't understand what.
So
I would like to remind people that orthogonal topologies, they cannot be classified. I mean, it's not like two-dimensional.
Indeed.
Yeah, but that's our problem.
So
That's not nature's problem.
So there are ways to make sense of the question in certain cases, and under this umbrella of caveats, is one supposed to sum over topologies in gravity, like in gauge theory, for example? Yes or no?
I don't know.
Okay. Roberto.
I don't know.
Bianca.
I would be super happy if I can do the path integral over matrix on a given manifold. And so that was kind of my primary aim for a long time. And only recently I looked, I discovered that the topology change could be important, but I'm also not sure. So I find that, so because of Jansen's comment, I find it hard to.
It seems like the various. Okay, 1 second. Seems like the panelists very sort of agnostic kind of answers. Let me give you my answer. Yeah. Renato.
No, I mean, maybe, but in absence of any good reasons, apart from people's gut feeling, one ought to be summing over everything, which is a total nonsense argument, in my view, because it's totally impractical. It's so ill-defined from any, conceptual and mathematical point of view, then that doesn't make sense. But that is what people tend to argue. Well, we should, because, otherwise, well, what would the path integral be? Well, it could simply be a path integral that describes dynamic etiology, which might still, in some interesting limit, describe things like topology change. And that's exactly what we are seeing when we do non-perturbative things. So even if you don't necessarily allow topology change at the outset, that can become part of your dynamical variables in certain limits. So let the dynamics decide.
Right. So I mean, I think there are many arguments in favor that are beyond like gut feelings, but we can talk about it separately. Yes, there is another question. Yes.
Yeah, I mean, my answer would also be no, but you need a variation principle that sort of does not a priori fix your topology.
Why? These are just totally different sectors to start with. Classically, these have nothing. Why? You should.
So
where does that should come from?
Well, we observe some topology, and we observe topology changes now with the formation of black holes. So
I haven't observed any topology change. Humanity hasn't observed any topology change of space-time.
So there's first Roberto raised the
I just want to qualify my I don't know. I don't know in the sense that the question is only relevant if you think that quantum gravity is the theory, is a quantization of a metric on a manifold. But I really don't know if there's quantum theory of space-time. Is there a manifold? Is the first question, or and then the question evaporates, so to speak.
So maybe you don't answer. You answer no to the quantum field theory framework for quantum gravity. Yes or no?
No, I answer yes because it's very useful, and it may be even there may be a quantum field theoretic UV completion. In that case, perhaps the answer one has to address that question. but it may also not, the answer may also be no UV completion of this form.
Yes, this is the reason also said I don't know, because you're forcing, that question implies that you first answer yes to the fact that quantum gravity could be a QFT, and then it's like a double question.
Also QFT of the metric and
But K meant sum over topologies, not really manifolds. No? Or it didn't mean smooth manifold necessarily.
Well, it's a sum over space-time.
Space-time, okay.
So space-time with a manifold which is not, it's not a product manifold of some three manifold times an interval of a real line. It's any four in the four-dimensional case, any four manifold, and then on each four manifold you then integrate. Then it's a path integral overall metric.
There was a comment, right?
Well, it's basically we are talking about summing over all geometries. Okay, whatever it is, if it exists, method exists, and if we really understand, if it can explain emergence of universe with statistically homogeneous and isotropic from whatever the geometry is origin, that is the goal. If we can explain that, yes, it's a right method. But if we cannot explain that and we just keep doing it in Euclidean space-time and be happy with that, then no.
Yeah, I was wondering whether your question, which is rather mathematical, whether we can phrase it more in a physics question, which could be, so maybe the question, do we think baby universes can nucleate or get absorbed by our universe? I think that's a more concrete physics question, because otherwise you're asking me some more topologies. I would say, for what matrix element, which partition function do you have in mind, right? Whereas the question, do you think baby universes can nucleate? That's an actual physical process, which is a topology changing process, no?
Yes, I mean, you can.
And then my answer would be.
So to make the question short, I've made it very short. So you could say, suppose you want to calculate the gravitational analog of a propagator from one 3-sphere to another 3-sphere. So then in that path integral, do you then integrate, do you include a sum over all cobordisms between those three manifolds? Which might include then baby universes which branch off and then reconnect, for example.
Maybe it has something.
But there are many, I mean, there's huge numbers of other sorts of cobordisms that are not of that sort. Right. And if you allow these, then you have to make some, some heuristic. I mean, everything, all of these questions have heuristic now. I mean, you have heuristic answers because we can't do the calculations. But what are we guided by? So the question is, what is your hunch, right? For such a heuristic calculation for this propagator, do we include just the trivial cobordism, which is just S3 cross the interval, or do we include do we allow other things? What's your hunch about that?
So really quick, because then Anna has.
You're asking me. I thought you were asking the audience. So I would say.
Then maybe.
Well, I'm not sure I'm prepared to answer precisely this question, but I had a comment that in principle, many things could depend on precise field theory describing gravity, if such exists. I mean, something which stands in your functional integral, because if the action is infinite, if you compute it on a different geometries, like different topologies or different, I don't know, black holes, which you can virtually produce in principle. If the action is infinite, then probability is 0 to produce them. For this reason, it could be already selected that what is preferred during the computation of functional integral is just something close to flat space-time. But this should be something which probably can be posed as a constraint on quantum gravity action, of course, if such exists.
The issue probably with that is that, I mean, you first need to sum over topologies and then you can say whether they are dynamically suppressed.
No. Well, I mean, when you are trying to compute effective action, first you can see what is the action. If you substitute if you take some particular space-time, I don't know, the whole or whatever, and in some theories, like for example, this is the state I'm referring to some recent results by Basile, that in quadratic gravity, for example, certain spacetimes have indeed infinite action, which suppresses their creation, nucleation, which is not happening in GR.
True, but that is a question that comes next. I mean, you can, so once you are summing over stuff, you can say whether that stuff is suppressed.
Yeah.
But in the first place, it comes to the question whether you are summing on those.
Yes, I understand the question. So my answer is like even if some it depends on the theory. Even if you sum over spacetimes, you still can have the answer that it doesn't matter.
But in the Lorentzian case, actually topology change typically comes with imaginary terms, and so these could be suppressed for this reason. Without you have to do the sum explicitly. Then there's still the question, it could be algorithmically that there's too many too many configurations, so you are algorithmically dead. That is still a possibility.
Good. So how? Oh, yeah, maybe after this could be the last thing, unless someone absolutely has to.
I had this question about black hole formation.
No, but Bianca goes.
Okay.
I had this. There's some work saying at higher energy you expect that black holes form and high Planck scale physics. And so I don't know what Roberto or John think about it.
I don't understand what it means.
What it means.
If you smash stuff really hard, it doesn't like form. That's the question.
So you take a high energy scattering of two particles, and
Yeah, those are quantum states.
Yeah,
and you're supposed to measure some quantum state in the end.
Yeah, so in the calculation, my understanding is at some point you make a semi-classical approximation, and so possibly part of the question is, do you think it's appropriate to apply this approximation?
You're asking me in particular.
Yeah.
I don't know, it may be, but I think I would be a bit wary of all these conclusions that one arrives about black holes. I think, how can I put it? I think one should first have know something more about the quantum theory, and then perhaps you can ask, what does this imply for the black holes? Whereas now, I think very often I hear statements about the black hole, and quantum theory is supposed to explain those statements or fit with those statements. Those statements typically come from semi-classical arguments. So why should we trust those statements so much? I think we should first develop theory, and then we can think of the black holes.
Did you want to say something?
Because I made a face.
Yeah.
It's just that if you have some proposal, like we will hear of what a theory of quantum gravity is, you will immediately see whether quantum gravity effects, by what scale they are suppressed. Okay, so typically, almost always they will be very strongly suppressed, and then you know that the semi-classical considerations that go into black hole thought experiments are actually very valid. This is why black holes have been our guiding principle. Like, for instance, quantum gravity doesn't have global symmetries. Okay, originally this came from a black hole thought experiment, and then in some cases where we can calculate toy quantum gravity theories in full detail, you actually see it perfectly how global symmetries are broken. So we just have seen so many successes of black hole thought experiments that I think it makes sense to say black holes first, and the rest should follow.
But those are thought successes.
No, but this I never understand. I think I don't understand this. We have this discussion, we keep on having it, okay? Are we okay with the Ising model in physics because it doesn't describe nature? You can discuss, are there phase transitions in the Ising model, yes or no? I can give you a theory for which I know it's not our world, but it is a theory which has the Einstein-Hilbert term at low energies, and we know it's consistent. And I can ask questions, can it have global symmetries? And I find it cannot. And a black hole thought experiment also told me so, right?
Yeah, but
I mean, I
don't
don't
is correct, right? These are thought successes, so it's fine.
I think so, yeah.
I agree, it's fine, yeah.
Yeah, but that's another question. But normally when we talk about quantum gravity, okay, we talk about Planck scale scatterings and all.
Yeah.
Well, I'm thinking in a cosmology mindset. If you say Planck scale, what comes to my mind is something pre-inflationary physics or whatever the physics that explains the same, something very, very short distance scales where you have very, very high curvature regime. When you reach high curvature regime, you don't really talk.
Yeah, no.
You are not precisely can say about something purely in the flat space time, Planck scale, Planck energy scale scattering. The picture is much more complicated. Crowd space time is important, and quantum fields in crowd space time is the most important thing we need to understand. So, just a comment.
All we're saying is that black holes give us a laboratory to see quantum gravity effects by doing thought experiments where curvature is extremely small. And that's what is so amazing about black holes.
Yeah, if we can do calculations following the thought experiment.
So,
we
may I ask
we
about the amazing result from black holes? So what is your opinion about the firewall, which is the most simple quantum effect of black holes? Is it there or is it not there?
Of course it's not there.
Of course it's not there.
Yeah.
So Don Mao, does he agree to you?
I don't know, but the firewall is the first thing you get the moment you have an inconsistent gluing of quantum states. I don't think there's any special something about it. I think it was a lot of hype. It just, the statement, the firewall paradox is just sharpening an existing precise statement of what the information paradox is as put forward by Matur, okay? So
there was a lot of hype, but clearly we were unable to decide what was right or wrong. Isn't that the correct statement? Because people do not agree yet.
There's pretty much a consensus that firewalls are not a thing. Am I?
but again, this is sociology. What means
Yeah.
a consensus? You can do probably a survey at some conference. It might be a loop quantum gravity conference, a string conference. You might get different answers. I would be surprised if there's more than 1% of the people taking a firewall serious. It was more a thought experiment showing that we did an
Probably right.
I think the discussion is going in a very philosophical way. The question is, I mean, we see at LIGO a waveform. Can you make a prediction of the waveform or no, using quantum gravity? But these are questions that should be answered now in some way. Not to, I mean, I don't know what you think about, but I never heard anybody talking about getting like a waveform in different theory of quantum gravity.
Well, there's many people doing this, like Massimo Bianchi and collaborators, right?
Yeah, you modify gravity, always
modify. I believe there is a problem that quantum gravity effects are Planck scale suppressed, so people just don't compute that because they say, I mean, unless you're screwing up your effective field theory, you're not going to see.
But do we have a prediction how to observe in the experiment or not?
I mean, in principle, one could write down something maybe in some approaches, but I don't know if people have done that explicitly in the sense that, I mean, you would expect generically from quantum gravity, now, independent of your precise approach, you are going to have at large distances where you can trust, effective field theory, you are going to have higher derivative corrections. And then the specific Wilson coefficients reflect your specific ultraviolet completions. Those Wilson coefficients, unless you have strong non-localities that come from quantum gravity, are suppressed. So they will impact the waveform by Planck scale suppressed effects. So I don't know if people want to compute them.
I think it's already rolled out. So there are papers on the S-matrix bootstrap and consistency conditions that tell us that these Wilson coefficients have to lie in certain regions. There's no way that we can, by seeing two black holes collide, see some quantum gravity effect from higher derivative corrections. That's
Anna raised her hand.
Yeah, I had a comment about observability of quantum gravity effects. It would be in principle possible if you consider cosmology and stage after between the inflation and hot stage of the universe, because all these extra EFT operators, which must be in quantum gravity in some sense, also extra couplings between inflaton field and gravitons, they can cause extra production of gravitons during in its most relevant during the stage, the transition stage from inflation to Riet. This is kind of inevitable, and the principle could be estimated and computed. In certain cases, it can quite strongly constrain the scale of quantum gravity, and also there are predictions for high frequency gravitational wave experiments. Not for LIGO, not for LISA, unfortunately, but for some high frequency proposals.
I have a comment. Why do we, everyone, many people think any theory, quantum gravity theory will formulate is only Planck scale? That is basically escaping from explaining any phenomena which would be relevant, can be measured in any near future. I don't think the Planck scale is a magic scale. Everything appears there. So we should be able to formulate theories and find new physics at a bit low energy than Planck scales. So
because below the scale you don't need quantum.
I mean, no, you need or not, but I mean, whatever we formulate, it will have implications lower energy scales. Why saying Planck scale, that's the only scale you see something is in something you say as an excuse to escape, and we do not help our observational colleagues to measure something new.
No, but
that's what they need.
You don't have a decision on whether quantum gravity creates observables effect or not. So I mean, if the right theory of quantum gravity is simply Planck scale suppressed, there is nothing we can do.
Why do we think exactly Planck scale? Why not give two orders of magnitude below the Planck scale?
Not exactly Planck scale. Depends on
biometrically, of course, numerically.
But yeah, we have to be precise, right? We can go a little bit, few orders of magnitude below the Planck scale and still try to find what's new the theories can imply.
Yes, because for example, in many theories, if you want to make gravity renormalizable, you need something else besides the graviton. So you don't just have one scale, you have more scales. And just to make the thing consistent, that would not be a direct test of quantum gravity. For example, a prediction from quantum gravity about the tensor to scalar ratio. That's not a Planck scale. But that's a prediction of quantum gravity, simply not really the gravity. The gravity part is there and it's making it, but the scale is not 7 orders below the Planck scale. So yes, I definitely agree with that. And of course, it will be sort of a desert.
Yeah, we did not
the high energies of CERN and the Planck scale, but something is there, definitely.
Yes. So I had one follow-up.
Maybe
Okay, I had also the new point, but so I will say the new point, but then you would decide if we just don't do anything. So the follow-up, just the follow-up regarding whether one can trust the high energy scattering of particles and production of black holes. That probably, in general, we wouldn't extract stuff, or maybe I mean that is not really the argument that convinces me the most, because I don't know if one can really trust the semi-classical arguments in the scattering, but there is an alternative argument which is based on the entropic reasons. So the fact that black holes, the formation of black holes is highly favored because they have huge entropy, which is the argument that Ivano explained me, and that is the most convincing in my opinion. And the new point, which is
going back to the argument that they form because they have a high entropy, but they don't.
They are entropically favored.
Okay, they do form in high energy system.
Or at least it's virtual resonances.
Virtual resonance, okay.
Yeah,
which affects the
amplitude. A little bit more convincing if one is.
I think Stephen Giddings is gonna be here at some point.
Yes, so probably we'll talk about that.
Yeah.
And the other point was really one thing that was mentioned at the beginning, but then we did not really follow up on that, and is microstage counting. And in particular, this was mentioned by Thomas, and we had like different reactions. I mean, you mentioned like that is very important, at least from what we understand from string theory. You can get the number right based just using the microstage counting. But you also, I don't know if it was you or Ivano, but you mentioned that in loop quantum gravity, maybe the number is not exactly right, and I would like to know like Bianca's opinion about that. On the other hand, Damiano said that that's completely irrelevant, and Roberto did not comment on that. So I wanted to understand a little bit better.
Yeah, so I guess logarithmic correction
as possible.
As big as
Yeah,
possible.
so
And then
I guess the
because-
logarithmic correction comes from a one loop determinant, which is a bit more dynamical. And the derivation and loop quantumgravity, the standard derivation, where it's very kinematical in some sense. You know, it doesn't really involve solving the theory. And so that for that reason, but I'm not surprised that you don't get the correct result, but I also I would not trust this calculation to give me the right one loop. I don't know, whatever that corresponds to.
You don't trust the effective field theory computation of Sen, or you don't trust the loop quantum gravity?
The loop quantum gravity calculation of that, because currently it is very kinematical. It does not involve solving the theory, not really fully quantum mechanics. So I wouldn't say that as a final result.
Right. And then philosophically, there's a question whether you should care about this or not. But I fully understand that you should say observations and nature first. But you cannot say things are allowed to be mathematically inconsistent. So the thing that's not sufficiently appreciated is the reasoning of internal consistency. So the internal consistencies can be so constraining. Although I hear all the time string theory predicts everything. Sorry, at the highest energy scale, one theory, 0 parameters put in. This is how strong internal consistency can be. So I think I am totally fine saying true physicists should put observations first, but we are also people that use the rules of logic. And logic means mathematics, and things have to be internally consistent. And for quantum gravity, it can be extremely constraining, and I think that's very healthy. And this is why I like toy models from string theory, which I know do not describe the world, but they're models in which you can study questions.
May I just add like one word is that like not just mathematical consistency with like, you know, first order logic, but with the physical principles we care about, like unitarity and causality and stuff like that. Like if you take them out, none of this works.
Yeah.
So that's I phrase it as physical consistency more than consistent with the physical principles that we care about at the moment. Yeah. Anyway, Damiano, please.
I don't know when did I say the time for physical mathematical inconsistency.
You were not impressed with the microstate counting, which is very impressive.
Equate logic with symmetry.
No.
Because it's against symmetry. Or I added that I'm against determinism. There are still some people who want to look for sort of hidden variance. Yeah. I'm all for uncertainty and determinism, but that's not illogic. I just want to say I'm all for mathematical consistency, but I have something to say about that. Because this is interesting, because I think that quantum field theory, going beyond the perturbative expansion for example, is a challenge. Okay, fine. Very difficult, very few results, very few non-perturbative things around perturbation theory. Some of them are right. Anomalies are exact to all orders, for example. But I'm starting thinking, as I told you before, that humans are just not capable to go beyond that, which means I think that there is a, exclusion principle making it impossible to a clump of atoms to grasp what's microscopic, period. So logic, what's logic? Logic is just a manipulation of sounds in our mind, and that's the result. But that's it. You learn it when you are a few months old, and you start building up. But I wouldn't elevate logic too much. But I'm against. I'm not against logic consistency. Bearing in mind, however, that I do not want to put logic as a principle. Coming back to principles, because it is not. It's just a tool.
I got a counter example to your argument about non-perturbative. Because I was thinking maybe perturbative is correct, but okay, let me give an example. So in De Sitter, if you compute if you take matter and compute gravitational loops, there are infrared logarithms which is computed by Richard Woodard, and for a long time he worried that these logarithms are not getting summed over. Then he applied the Stravinsky stochastic technique, which leads to non-perturbative resummation of all the terms. Then you get a finite answer. So we do have progress in understanding non-perturbative resummation and getting a finite answers in the case of Digital.
I will talk about examples myself tomorrow. I agree. Yeah. And one is key for my prediction, by the way. Without that, I wouldn't be able to extract it from perturbative quantum field theory. I have to mix it with cosmology, which by chance gives me one sort of non-perturbative information. But still, the galaxy is perturbative quantum field theory and some splashes of. Think of the progress we made as humans in defining the functional integral as a concept, mathematically speaking. That's why I'm started thinking maybe nature is tailored to predict there is an intrinsic obstacle. We are macroscopic, and it's like famous problem of Einstein when he asked himself to measure time. You have a clock. Clock is big, it's macroscopic, right? So what is time? Going back to our question before, at the microscopic level. I mean, there is no time.
Good, and there is no time. Yeah, looking forward to the rest of the workshop. Thank you.